Today I'm going to talk about union and find operations on the union find data structures. The first thing I'm going to talk today is bijection. So we'll start by creating a mapping, bijection also known as mapping between our objects and integers. And the second part, next, we'll look at the array constructions. We'll construct an array where each index corresponds to an object via mapping. And additionally, we'll look through the process of unifying of groups. So this involves changing of values in the index array to assign elements to some group. Now, after that, we'll discuss how to find the root node of some component, of a given component. So, in fact, we'll look at the find operation. And next, we're going to look some general observations or remarks, some facts that are need to know while working with this data structure and using these operations, union and find operations. Okay, so the first thing I wanted to talk is that the creation of union find data structure. So to begin, we're going to begin using this union find. We first need to construct bijection, that is known as mapping between the objects and the integers in the range from 0 inclusive to n non-inclusive. So this isn't strictly necessary, but it lets us use a simple and efficient array-based implementation. So a bijection is we can refer to as where every element corresponds to only one element. So here the root node would be a self-looping or self-rooting element. We'll look at it a bit further. And now we can arbitrarily or randomly assign a mapping between the objects and the integers on the right. So these objects would be the integers, and on the right we'll assign some integers, that is the index, to these objects. So we'll usually store these mappings in a hash table for easy lookups. Okay, now let's randomly assign these. We're going to store these mappings in some sort of mapping, this hash table, a mapping object such as a hash, for example, hash table. And now, store union find information in an array. We can store and we can represent the union find as an array. So each index has an associated object. So letter, here we have a letter. So this is and we can look up through our mapping. So here, using an array, using this an array implementation using hash map for when we assign to every element. Randomly or arbitrarily, when we assign index, we can use an array implementation, and that would be pretty useful for us to implement it in this way. And now, so what we can see on this picture, on this slide, at the top, that is the array we have just created, which contains our mapping. Contains our mapping or bijection. So here we have the elements and the indices. So we are going to change them as we are creating groups. So now, at the center, this is just a visual representation of the graph or of what's going on. And the value on in the array for each position is currently the index, which is it. And also, this is because originally every node is a root node, meaning it maps to itself. So the root node of every node now at this moment is itself. It's the node itself. So that is why it is in this way looped. And on the left we have the instructions we're going to perform. So that is union instructions. So we now after all these instructions are done, we'll get some disjoint sets. So also we're going to find that we're going to change the values in our array to map to other letters. So in this way we're going to do it for some index. So by the way, we'll do it to assign some element to the group. Okay, now let's look at an example on using these instructions on the left. So now the first instruction is C and K. So we either set the value at index 4 to be 9. So yeah, we can see that the value on the position 4 is the K is at position 4 and J is at position 9. Not J, but K is at position 9. So here we want to merge the smaller group into larger groups. So we are going to do this in this way. So we are changing changing values. So we want to unify C and K. So we choose K's parent to be C. Now the K's parent is C. That's right. The case parent is C. So we are assigning to K node index 4, since the index of C node is 4, and we can see it on the second array on the array beneath or under the array of letters. Yeah, and so in this way we can create groups, these graphs. And now, for example, next for F and E. So we have F at the position 1 and E at the position 0. Yeah, and now F's parent becomes E. So F is at index 1 and E is at index 0. So we update index 1 to 0, and in this way we are assigning into the group. We are assigning E and F to the same group, for example, red group. And now then for A and J, the same thing. We're performing a union so the A's parent now G. So we are assigning both of them to the index 6. Since initially the index of A is 5 and index of J is 6, so we are now changing every index to 6, since now J is a parent node. But here where things becomes a bit more interesting, because here we want to want to unify indexes, or not indexes, but elements A and B. So if we look at A has a 6 in itself, so A corresponds to 6, but B is but 6 is J, also J. So here the root node for green group is J. And B is B here is a single node. It is self-looped or self-rooted node. So we're going to merge smaller components into larger ones. We want to merge them, or unify into unify them, or combine them into groups. Now B is going to become the child node of D. That would work in this way. So since we generally now since we want to
it's going to become a member of another disjoint set.
Yeah, that's right. It's going to become a member of the set, and the root node of this set is D. So we are, that's right. Then we unified A and B by assigning both of them to the parent node that is D. Okay, now.
And just one question for you, for my edification. The number on the bottom, 0, 1, 2, 3, 4, 5, 6. Okay, so that is the original group number, or that's the original group number for each element, correct? Because they
yes,
all began separate. They all began as separate groups, right? They were all. You had 11 disjoint set, or 12 actually. 12 disjoint sets at the very beginning, correct?
Yes. Yeah. So here that is what it was initially. These from 0 to 11 on the bottom. That's it.
Okay.
Their initial group.
Okay. Yeah. I just want to be sure. Yeah. Okay.
Yeah. That's right. That is under the indices of the groups. We can call this in this way. That is their original indices. So okay. And now we want, for example, to merge C and D. C is the root node. For example, K. So and the root node of D is D. So the self-looped node. So here we are going to merge C and D into a larger group, a larger component. So that is the orange group. So here we don't want to, for example, combine orange group with D in the way to add to D. This orange group. However, we want to D become a part of the orange group. Not opposite. So in this way, we are assigning D to C, and now D is a child node of C. Now, next, D and I. So we want to merge D and I. So we do a similar thing, and now I points to C. Yeah, that's it. I points here. I forgot the word. Points to C, and now for example, we want to merge L and F. So F's parents is E. We can see, and we're going to merge L, which is self-rooted to E, and now the E is a parent node of L. Yeah, that's it. So the next instruction we want to perform is to union C and A. So the C is a here. That's also an interesting example, because if we find, for example, the root node of C, that is C, because C is a self-rooted node, and for example,
it's a self. Okay, so if a node is self-rooted, does that mean it's the vertex, or is that okay, so if you didn't, for example, if you did not have your diagram, Okay, so we have your diagram and we also have your array in your display, in your demonstration, right? Let's say you only had the array in your demonstration. Would you still know what the root node was? Or do you need your
So
display?
here
You
I
understand
think
the question?
yeah, I understood the question. Thank you for the question. So here I think you that is at the center of the middle of the screen. That is the we can call it the where that is just the I think that is the example
Mm-hmm.
of how we can show that, or what's this word yeah, how that is. Oh, one moment here. That's interesting. So,
I understand
uh,
how it works, but you have your display. Your explanation is good. Okay, but what my question is that you rely on your display, right? Okay, to know which node is the root node of a set, right? Of a
yeah.
disjoint set. Okay, but I'm saying, what if you didn't have your display? You just had your array like you have at the top, right? Would you still know the root nodes? Okay, so I'm a little bit confused on that topic.
So I think that is the middle. That is the representation. But here I think the root node is that is so for example the index of the every element in the yellow group or the or orange group, or yeah, that is 4, and the initial index of C also 4. So I think that the this assigning the root node, yeah, works in this way
Oh, so
because
if the index, the original index matches, then it's the root node. Okay, right? 4, 4, 6, 6, 8, 8. So that's always the root node then, correct?
yeah, so yeah, I think that's it, yeah.
Oh, okay, yes. Okay, I understand now. Okay, I'm sorry. I
Okay,
want to make sure I
thank you for the
understood.
question.
Okay. Okay. Go ahead.
Okay, thank you. So, for example, now we want to unify A and B. So, if we, for example, go up and follow the parent nodes of A, for example, the parent node of A here is C. So, the parent node of A is G, and the parent node of G is C. Uh, yeah, so here as we reach the root node. So the root node here is C. So the parent of C is C. So in this way, we know that A belongs to the orange group. Uh, yeah, because the index of A on the yes, middle array, if we can call it this, and if we can call it this way, that is 6. And the we now look at the which node at which index corresponds the element that initially was at the index of 6, and here we can see that initially at the index of 6 there was a J node that now has index of 4, and 4 is C. So in this way we can understand that A belongs to the orange group, to the group with the C with the with its root. Yeah. So A is the parent node of C. The root node of no, not C is a parent node of A, because so the root node of A is C. And if we do the same thing for B, the root node of B is D. So as the index of B is 6 again, and the element that was on the position 6 initially is G, and it is yeah, the root node, the parent node of G of this node is C. So, and the parent node of C is C. So that means that is the root node, and we can, in this way, we can understand that the root node of both A and B is G. So, or not G, but C. So in this way, we discover that B's parent are also C, and that means that they are on the same group, and we do not have to combine them. We don't need to merge them to unify them. So since they are already unified with the with the orange group. And now the next we want to look is H and J. So they currently don't have any group, so we are going to arbitrarily merge them into the new group. This way, that is the blue group. And now, we want to combine H and F. So we're looking. So if we look, we can understand the parent of H, and we can see that we need to combine it with the red group, because F's parent node, or F's root node, the root node of the graph, the Fn, is E. And E is in the red group, so we want to combine blue and red group, and we want to combine to the group that is larger. So here, red group has 3 components, so we're going to merge the blue group into the red group. So now we make the root node point to E. So in this way, we point to E, and which is now the root node of these 3 parents, of the 3 children. Yeah. And now we have combined these into the red group. And now the last instruction is to merge H and B. So H's root node, as we know already, is E, because it is on the red group. And if we follow up the chain from that's H, D, and E. And the B's root node is C, because we can go from B to its parent node, and then parent node now is C. So now, since the orange component is larger than the red component, we're going to point the root of the red component to the root of the orange component. So now E now points to C. In this way, we have merged all the elements into one large group. So that is this orange group. So also here in this example we are not using the technique that is called path compression. So because that is used for optimization of the union find, and we're going to look at it at the next talk. So now let's look at the summary. So we have now looked at 2 operations, that is find operation and union operation. So the first operation is find. So to find which component a particular element belongs to, we need to find the root node of this of this component. So if we want to to classify or determine to which group belongs some particular, not some, but a particular element, we can follow its parent node and the parent node of the parent node, etc. So until a self loop is reached. So that is, for example, as in the previous example, when we reach the C, for example, and the parent node of C is C, that means that we have Now look, we have reached the self loop component, self loop element, and this element is, of course, the root node as its parent, as its parent is itself, and the union operation, to unify two elements, we need to find which are their which root. We need to do the find operation to determine their root nodes of each component, and if root components are different, we make one of the root nodes to be parent of the other, and the parent here would be the group that is larger. So in this way, we can unify two groups, for example. But if the important node here, the important note here is that we found that two components that want to unify has the same root. That means that they are already unified, and we don't need to do this. Okay, now the last thing is some remarks, some fact that we need to know. So within this data structure, we do not ununion elements. So by the way, in general, we can do this, but it would be very inefficient, since we would have to update all the children of a node. So that is pretty inefficient to ununion elements, but there are no, but there are very, there are almost no, we can say that there are almost no practical cases, implementation, or practical cases, use cases, if we can call this in a way, of these situations when we need to ununion elements in this union find, because more often we need to union elements, we need to unify elements into the group, we need to merge them into the groups, but not break these groups. And the second note that the number of components is equal to the number of roots remaining. And also the number of roots never increases. So to put it in other words, the number of components is equal to the number of roots remaining, or also, and also I think here would be true that the number of components is equal to the that's it. And also number of roots never increases, root nodes never increases, because we do not add new elements, we only union them. It works this way. So by the way, that is the end of my today's talk. Thank you.
Okay.
I'll wrap up here.